Alright, silly people, here's the situation. We're going to be calculating a bunch of Lorentz invariant quantities, um, which all depend on various forms of the electric strength tensor um, for E and M. So the first invariant that we calculate is this guy, this F to the alpha beta sub F alpha beta, um, which is just the strength tensor multiplied by the covariant form of the strength tensor. So, I'm just looking um, at the matrix forms that Jackson writes down in that chapter, and running over betas. So I'm running over columns. So all of the stuff in the first column times all the stuff in the first column of the other matrix will just give you minus e squared. Then you look at the second column, and you have alpha alpha 1, alpha alpha 2. Um, those look like minus ex squared plus bz squared plus by squared. Okay, and then running over beta equals 2, we have minus ey squared, and then a bz squared, and then a bx squared. And then final column, I just have minus ez squared plus by squared plus bx squared. Add all these up. Looks like we have a minus e squared here and a total of minus e squared here, and then a couple of factors of each component of the magnetic field squared. So we just get minus 2 times the square modulus of the electric field plus 2 times the square modulus of the magnetic field. Um, that's all cool. The next invariant that we want to calculate is the dual strength tensor times the covariant form of the strength tensor, which is going to be just running down the first column. We have f tilde alpha 0, f alpha 0. First column just gives you e dot b. Next one it gives you also e dot b. I'm noticing a pattern here. Alpha 2, we have alpha 2 also e dot b. And then finally the third column also e dot b. Okay, so then the total is just 4 e dot b. That's fine. Then we're also asked to do the dual strength tensor multiplied by the covariant form of the dual strength tensor. And Jackson doesn't actually have written what the dual field strength tensor and its covariant form is. So I'm just going to get that first and then do the rest. So f tilde sub alpha beta multiplying by the Minkowski metric on both sides to turn it into its non-covariant form. We'll just let's write all of this out in matrix form because it's going to be a kind of an easy matrix multiplication. So this is the Minkowski metric that I'm writing right now on the right side, and that should be a 1 there. And then the dual strength tensor is just you got actually plus signs on the first column, bz, and then we got minus bx, 0 minus ez ey minus by ez, 0 minus ex minus bz minus ey ex, 0, and then multiplied by the Minkowski metric again. What that is going to do is it's just going to first flip the sign on the first column, so all of these are going to become minus signs, just evaluating the multiplication of these two matrices. And then when you multiply that with this other side, it's going to flip the sign of the top row. So all you really did is exchange signs between the first row and the first column. So this is going to be 0 bx by bz minus bx minus by minus bz, 0 minus ez ey ez, 0 minus ex minus ey ex, 0. And that's all very cool. Now we can actually calculate the invariant, just looking back and forth between Jackson and my form of the matrix. We have that f tilde alpha 0, f tilde alpha 0 is just minus the square of the B field. And then we have f tilde alpha 1, f tilde alpha 1, just looking over the second columns of each, minus bx squared plus ez squared plus ey squared. And then this thing, alpha 2, we got minus by squared now, we got plus ez squared, and we got a plus ex squared. Let me change that to ex squared. Last column, we got alpha 3 is just going to be minus bz squared plus ex squared plus ey squared. Okay. So summing all of that up, it just looks like minus 2 times the square modulus of the magnetic field plus 2 times the square modulus of the electric field. So actually nothing too exciting there. Then the question asks, can there be a situation in which the field is entirely electric in one frame and entirely magnetic in the other? And the fact that we just calculated a bunch of Lorentz invariant quantities is important to this. So we found that f alpha beta times f sub alpha sub beta equals minus 2 e squared plus 2b squared. And this is a Lorentz invariant quantity. So it's equivalent to write the e squared and b squared of a different frame related to the first frame by a Lorentz transformation, right? Okay, so if the field is entirely electric in one frame, then we have that the left-hand side of this equation is 2b squared. And then we're going to let it all be magnetic in the other frame. Or, I mean, no, this was all magnetic, and then this can be all electric, so this will be minus 2 times this thing here. Which means the right-hand side of the equation is greater than 0, or the left-hand side, fuck me, left-hand side of the equation is greater than 0, because the square modulus gives you a positive number, while the uh, right-hand side is less than 0, because, again, the square modulus gives you a positive number, which is a contradiction. You can't have something be positive on the right side and negative on the other side, unless if they're both 0, in which case that kind of contradicts the whole point of the thought experiment. So no, you can't have a frame where it's all electric in one field and all magnetic in another field. The problem also asks, uh, what if the field is entirely electric in one frame? What are the criterion for the other frame? And all I'm thinking about is this Lorentz invariant. So if it's entirely electric in one frame, then on the left-hand side we can write it like this. And on the right-hand side, we'll have minus 2 e prime squared plus 2 b prime squared. So that sets a condition on what the strengths actually are of the fields in either frame. And I'll just write it as that the magnitude of the field in one frame better be equal to minus the electric field in that frame, in the other frame, plus the magnitude of the magnetic field in the other frame, both all squared. So that's the condition. Then the problem is like, okay, let's define some more matrices. Specifically, it's like, so if we want to form a matrix, which is the strength tensor, we form it from E and B. And then what if we wanted to form another tensor from D and H? The equivalence of E and B that's just in a macroscopic medium. So I'm going to form this tensor, G alpha beta, but I'm just going to make symmetry arguments and just have E go to D anywhere an E shows up, and B go to H anywhere a B shows up, and write every form of this matrix that we want to look at. So this is going to be the macroscopic field strength tensor, which is minus dx. It has all the same properties as the other field strength tensor. It's now just talking about within a medium. This isn't a completely useless exercise, but it's kind of useless. And then the covariant form you just get by switching the signs on the first row and the first column. So I'm just actually going to copy this down. No, it's not completely useless to do this problem, because if you're talking about doing relativistic E&M in regimes where the permittivity is not linear, then this may be a useful thing in that. But given that most every medium out there, especially when relativistic fields are concerned, you really don't care about the nonlinear regime for permittivity. My God. Because most materials are linear anyway. Then the covariant form of that, you just switch the signs on the first rows and the first columns. Minus, 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 plus, 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 minus, 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 plus, plus, plus. These are looking good now. So there's going to be some more invariant quantities given these. Um, one of them is going to be just the macroscopic field strength times its covariant form, which I'm going to argue by symmetry is going to look the exact same as the other thing for the non-media form of this covariant and look like that. So just replace E with B, or E with D and B with H. And then the same goes for all of these invariants. So this is going to be 4 times D dot H, and this is going to be 2D squared minus 2H squared. There's also going to be a class of identities where you have combinations of the macroscopic field strength tensor and also just the regular field strength tensor. Of which there are a handful. But I'm just going to argue symmetry in all their cases anyway. And replace anywhere where an E squared shows up with an E dot D, and anywhere where a B shows up with a B dot H. So it's going to be minus 2 E dot D plus 2 B dot H. For this guy, you get 2 E dot H's and 2 B dot D's. Same thing here. You get 2 E dot H's and 2 B dot D's. And here you just get 2 E dot D's and minus 2 E dot H. So all of those quantities are also invariant under Lorentz transformation. All right.